this is equal, I'll have a series of boxes on the right to save space, log a Vn plus lambda n minus 1, right? It's long-lived log. This is then, the idea is to open this up with the binomials. Remember, we want to be able to do the integral, right? The only way to do, the most natural way to do these integrals is one term at a time in the against powers of lambda. So, okay, binomial expansion. So let's see. How does it go? It's 1 minus k. Okay. Let's see if I remember my binomials. K, A, V, N plus, oops, lambda k. All right, so this is a box that's useful. I guess if you really don't remember, n minus 1 minus k dk n minus 1 minus k factorial 1. Okay? Another box. Right, so this integral then becomes, so the integrals are gone. N minus 1 and n minus 1 will eat each other. And so this becomes much better looking expression. I left off the sum, but you can put that in your own notes. Log k a v n k factorial v n 2a. All right. So this is an interesting sum. It has a k factorial in the denominator. That's always a good sign that you can converge almost anything with a factorial. But it has, remember, we're interested in n goes to infinity limit. It has n inside the logarithm. So this is actually not necessarily a convergent series. I guess I just ignored that because it's done on the positive things. As n goes to infinity, that you're just covering the entire. Yeah, I mean, I'm just assuming that v is small enough that you're going basically, right? You're going all the way to the 0. Okay, if I wanted to introduce theta function here, the cutoff, there will be a small lambda cutoff on the integral. That's logarithmically small or large, actually, I have to check. But okay, so I ignored that, I don't think it's V, oh, sorry, I defined that last time. So V is disorder. V is, I have to look at my notes. It was a factor of 2 or something, maybe. Give me 1 second. Just no. Where was it defined? I did define it before jumping to the next stage. Okay. No. I don't see it now, but let me just guess that it's V over T. By V, sorry. W, right, so I did not define the distribution of these guys, but the width of the distribution was W, so it's W in the hobby. I think there was a factor of 2, I don't remember. What? T over, no. Little v, oh, was it T over W? I'm sorry. V is, yeah, okay, sorry. 2T, okay, fine. What, this? To the minus 1s, yeah. So it was, this was there to begin with. Once you do an exponential substitution, you get a to the first power e to the plus lambda and cancel. Okay. Right, where am I? Yeah. So, the idea is to, let's focus, right here, let's focus on the n goes to infinity limit by changing variables, right? We want to take that sum and not treat the large n thing as just another limit. We want to somehow pull it out, right? And so the idea is, let's define k, let's define a new variable by relabeling new variable L by this, that's fine. And the idea now is that if we assume that L is much, if we look at small L limit, we're essentially sort of asking about the behavior near the top range of that. Almost finished with this part anyway. Let's see. The idea is that then we can ask about, well, then we can certainly use the Sternberg formula for the factorial. Please try to follow the, I don't think I have any stupid mistakes, but one never knows. Minus L minus 1. Right, and so now, having made this approximation, well, I haven't made an approximation yet, but now I'm going to make an approximation of throwing this out. Right, so one, I'm trading the factorial of this guy, I'm approximating with a factorial of n minus 1, assuming that L is small. Right, this is not mathematically rigorous in the sense that I am reducing, this thing, I'm ignoring the thing which is bigger than 1. Right? You might worry about that, but that's, the idea is to, well, the idea is to finish one calculation first. Right. So is there anything else I need to tell you? Well, it's en root 2 pi n log 1 over v plus log a over n. We're almost done. Okay. And now we are done because we can, well, en root 2 pi. By the way, all of these power law prefactors are, of course, irrelevant. We're basically trying to gather up all of the exponential dependence on n. Right, so now I'm pulling, the idea is that now that v is small, so this is large, I'm going to pull this out. And I'm going to re-exponentiate this guy. So it'll be log a over n. This is sitting there. Okay. Approximations galore. Again, let's say that L is much, much less than 1. So that's great. Because now we've taken this beast with n dependence mixed in the under the logarithm, and now this is sort of everything has been factorized. We can do the sum upon L. Another box. So the idea is that this is just a geometric series, and the sum upon L of log n minus 1 minus L, that's just log n minus 1. Okay, so that's it. Oh, sorry, whoops. I'm just paying attention. All right, remember the sum of the geometric series is 1 over 1 minus x, and so we're in the regime where x is large, so it's basically we soak up we soak up that 1 power. Okay, so let me just collect the answer. Absolutely. Thank you. Very good. Yes. And that's going to be important. Well, marginally important. All right, so we're finished. So just to collect, so n, remember the integral that we had to compute was n times this integral. This n is Cn, Kn, where k is that 4.5, that lattice dependent sort of phase space thing. Now I'm going to copy -1 plus log. So people have complained about the shadow. I probably shouldn't do that. So David Hughes complaining he's not here, so maybe he was channeling. So I'm just copying things from, what did I do? The rest of it. Right. I'm now starting to copy things from here, and then I will paste in the value for this sum that was computed. En log n, sorry, log n 1 v. Well, okay, at least I copied everything that's in my notes. Now let me just check to see that this makes sense. So the probability on the sum of these paths, then, as we just said, it's d by dA e to the minus this integral. And you can see that the only a dependence is to this factor, so that's easy. So, so I will write it as e to the minus 2 plus log 1 over v. So you can see that I'm defining a thing that's independent . Okay, where I've defined this quantity which controls what the distribution does as n goes to infinity. Okay? Now we're done, because if x is bigger than 1, then when n blows up, notice nothing else depends on n. There's just one knob. When n goes to infinity, if x is bigger than 1, this blows up, and the exponential becomes, well, because there's a minus sign, the whole distribution just flattens out and flows. So if you start with some intermediate n, not equal to infinity, as you push off to infinity, it becomes, distributed. So it seems like you cannot stop at some low path, finite length path approximation. So when x is less than 1, as you raise it to the high power, you can ignore the exponential, and it becomes a distribution which is x and, clearly, there's no, I have not worried about normalization. We're talking about just the shape of the distribution. And you can see that the distribution becomes highly peaked at small a, and sort of it's not saturating, it's not spreading out, so it's peaked at small a's, and this is localization. And there is a transition, so x equals 1 is a transition point, so I'm doing this again, VC log VC is equal to 1. So these kinds of functions one can solve approximately, that it's log 1 over EKC, I guess, This turns out to be, what did I say, 0.025. Okay. So this theory is right about some things. It's wrong about everything else, obviously. What's right? Localization is stable, self-consistent, depending on your perspective, consistent, the estimate for DC is good. For large enough dimension. So this belief is based on trying to estimate paths that have been ignored. I'm not going to talk about that. This is, as far as I know, this is not something that's very well understood, but that's the belief. It's much easier to talk about what's wrong. You know, those of you who have done some something with condensed matter systems generally, what we're doing here is we're computing, we're trying to locate the phase transition. And first of all, you don't expect to be able to do that exactly because the location of the phase transition is generally not universal. Right, so the value of VC is never going to be correct, and it's only with tweaking of the model and making things artificial that you can make it exact. So that I'm not even going to put that down because that's sort of self-evident. So this is a critical point, right, where something changes, the conductivity just turns on. So one can ask questions about critical exponents. And they're always wrong, or almost always wrong when you obtain it. If you try to estimate critical exponents by Taylor expanding about the critical point. But there's actually a much more profound problem with this approach. It actually predicts transitions in, transition when there isn't any. Transition in 1 and 2 dimensions, and there aren't any transitions in 1 and 2 dimensions. It's just the carry. So what the lesson from that is that there's a certain approximation that one uses here, and this approximation is just that. It's an approximation, and so one has to somehow figure out how to complement the analysis to, to study, places where. So by the way, this was not, as far as I know, this was not. Yeah.
Why is it predicted transition in 1 dimension? In 1 dimension, there's only one path.
Oh yeah, in 1 dimension. In 1 dimension, there's only one path. So you're saying that the distribution will not. I guess I was thinking more generally if you had further neighbor hopping and things like this. I see, so in 1 dimension it wouldn't predict the transition? I haven't actually, yeah, that's right, there's only one, non-retraceable, there's only one path. But what if you include, so wait, so for one path it would not give you a transition, okay, so I'm just thinking in 1 dimension, oh, the exponential disappears, that's right. My apologies. Is it really? So if I introduce next nearest neighbor hopping, will there still be only one path? Okay, okay, at some point I decided that in a more general setting where you have further neighbor hoppings, even in 1 dimension you can get a transition. But I haven't checked that. Or rather, I haven't found any